Okay, so a student designs an experiment to study a reaction. The reaction is represented by the equation above. The student places 2.24 grams of sodium bicarbonate in a flask and then adds this acid, and then we're going to form bubbles and the flask gets cooler. So forming bubbles means that you have a gas being formed, and then the cooler means that it's an endothermic reaction. All right, so that's good knowledge. We'll take it into the question. Identify the reaction represented above as an acid-base precipitation reaction or a redox reaction. Okay, so everybody agree that it's an acid-base reaction? This is the acid. And then this one is the base. All right, and then we can tell that we're not really changing oxidation state. So it's not a redox reaction. Okay, so acid-base chemistry is not on your exam, but I think that being able to tell that what type of a reaction it is I think within the realm of possibility, because I think most of you guys learned that pretty early. All right, based on the info, identify the limiting reagent. All right, so we have to set up two sets of stoichiometry here. All right, so I'm going to start with my 2.24 grams of sodium bicarb. All right, I'm going to convert to moles. All right, so 84 grams in 1 mole. All right, that's using the periodic table. All right, and then I'll be a little careful here. All right, and then we can go to any product that you want. And I'm just going to keep it in mole to mole ratio. So 1 mole NaHCO3 would give me 1 mole of water. All right, and then if I chug the numbers here, 2.24 divided by 84 is 0.0267 moles of water. All right, now I have to check the other reagent as well. So I'm going to start with, you always start with what you're given. So I'm going to go ahead and convert that to liters. So that is 0.06 liters. All right, and then the molarity is 0.875 moles per liter. All right, and then this is of my acid. And then I'll convert to moles of water again. So 1 mole of HC2H3O2 for every 1 mole of water. And when I multiply across the top here, I get 0.0525 moles of water. All right, and so this one is the actual yield. So this was my limiting reagent. All right, I got less of it. Okay. Does anyone have any questions on that question? So then just by way of like what could you have done, you could have picked any of the products as long as you were consistent. You want to convert to the same product. It would also be okay to just go to moles of whatever the reactant was, because everything's in a 1-to-1 ratio. So that was also okay in this one. All right, but not necessarily okay in all problems. Okay, so for part C, the student observes that the bubbling is rapid and then gradually slows. Explain this change in terms of collisions. So this is a kinetics question. So remember that the rate of a reaction is going to be equal to some rate constant K times the concentration of whatever your substrate is. All right, substrate here is equal to reactant. So as I'm going through my reaction, I'm going to have less concentration of my reactant, and therefore I'm going to have less collisions between those molecules, and therefore the rate is going to slow down. Okay, everyone good with ABC? Yes, no? This is 2016. All right. In thermodynamic terms, a reaction can be driven by enthalpy, entropy, or both. And then we want to know what is guiding the reaction here. So, okay. So I'm going to do the justification first. Delta G is equal to delta H minus delta ST, the ghost equation. All right, so we know that we're going to have something that is favorable when this is negative. All right, and then we're told that this is getting cooler, so we have an endothermic reaction. So then we should remember that if your delta H is positive, then we call that endothermic. And if delta H is negative, then that is called exothermic. All right, the way I think about it is that for the endothermic one, the heat is a reactant, and then for the exothermic one, the heat is a product. So this is positive by definition. All right, so in order for this to be overall negative, then this must be greater than that. All right, and so this must be a positive number. All right, it's not possible to get a negative number if this is not a positive one. So this would be entropy only. Any questions? Okay, great. Okay, so that's a good question. Good question. So the question is, how do you know that delta G is negative? So I'm assuming that because the reaction is occurring, that it's a spontaneous reaction. AKA, we're not adding energy to get the reaction to go. Does that make sense? And then in general, when you get a question about thermodynamic favorability, you sort of have to be favorable in order to get, the reaction to go. All right, now that said, if you're putting in energy, then that's a different situation. Okay. All right, so next question here is looking at the bicarbonate ion. So we have 3 carbon to oxygen bonds. 2 of them have the same length, and the third one is shorter. So we're going to do a Lewis structure, and then we're going to basically make sure it's consistent with the description. All right, so now remember that carbon really likes to make 4 bonds, and it likes to have no lone pairs, okay? So I'm going to try to get that central carbon to follow that criteria. All right, and so I need to attach 3 oxygens to it. The only way I can do that is to do that. All right, and that satisfies the criteria so that I have 4 bonds and only 0 lone pairs. All right, now oxygen in general likes to make 2 bonds and have 2 lone pairs. All right, I'm going to go ahead and attach the hydrogen, and then I'll fill in my oxygen electrons here. All right, now the little guy that's over here that has the one bond, all right, this is the oxygen that has the formal charge with the negative. All right, so the negative is sitting on that oxygen. All right, and so then when we look at the molecule, all right, we can see that it's impossible to distinguish between the left oxygen and the right oxygen having the double bond. All right, so we can draw an equally favorable structure where the other oxygen has the double bond. All right, and then the right one now has the extra lone pair. All right, and so now this guy is the formal charge. All right, and we're still overall negative. Now, to comply with the description here, this one and this one have the same length. All right, because each of them have 1.5 bonds, they're being shared. This is called resonance. All right, so it's impossible to distinguish between them. Okay, so these little guys down here have what we would say is a bond order of 1.5. All right, it's half a single bond, half a double bond. All right, this one is the one that is shorter. All right, it's only possible to draw a single bond there. All right, so that only has a bond order of 1. Okay, does anyone have any questions? This is being recorded, yes. You can tell by the little red button that says recorded. Okay, so part F is a acid-base question that is not going to be covered on your exam, so we're not going to worry about it. Does anyone have any questions on anything that's on the board right now? So we're going to do the questions that don't have to do with applications of thermodynamics. All right, so we're going to do everything else. So first part is determine the oxidation number of Cl and NaOCl. Okay, so the way that we're going to do this is you assume that anything that is in a, well, okay, so the sodium here is going to be +1 because it generally has a charge of +1. All right, and then the oxygen is going to be -2 because it almost always has a charge of -2. The only exceptions here are that you have, when you have O2, all right, elemental, it has an oxidation state of 0. And H2O2, these guys are +1, there are 2 of them. And so these guys must be -1 to compensate. So those are your only exceptions. All right, and so then in order to get this thing to balance, that chlorine has to have a charge of +1. All right, and so let's see. What are the number of grams of that compound in order to prepare 100 milliliters of 0.5 molar? Okay, so I'm going to start with what I'm given, which is going to be the thing with 1 unit. All right, so the 0.1 liters. All right, so 0.1 liters times 0.5 moles per liter of your Na2S2O3. And then in 1 mole of Na2S2O3, All right, so sodium is 23, sulfur is 32, and then oxygen is 48 total. $158. So there's 158 grams in 1 mole. Multiply across the top and divide by the bottom. So this would give me 7.9 grams. All right, so that's a pretty easy stoichiometry question. Hope you guys get a lot of those. All right, any questions so far? Okay, so, all right, so let's go ahead and use a balance equation for the redox, and then our information here to determine which one's the limiting reactant. All right, so it looks like we have the same concentration of everybody. And so if we look at our balanced equation, I need four NaOCl, 2 NaOH, and 1 of these guys. All right, so I need 4 times as much of the NaOCl. Since I'm starting with the same concentration for all of them, all right, then my NaOCl was my limiting reactant. All right, does anyone have questions on that question? So I'm going to skip the rest of the question because that would be an application of thermodynamics, which is not covered on your exam. Okay, so I think we'll go through number 2. It still is thermodynamics, but it's not an application of thermodynamics, it's just straight thermodynamics. A little blurry. So does anyone have any questions before I put up a new question? Okay. Okay, that's a little tiny. All right, hang on. We'll kind of put it and then zoom in, I think. Okay. So let's start the question. So we're looking at a reaction of nitrogen oxides. And so we're looking at an equimolar mixture of NO and NO2. Okay, so particle level representation of the mixture is shown at the box on the right and the box at the left. We want to draw the representation of the reactant mixture of NO and O2 that would lead to the product mixture. Okay, so does anybody have any clue what they're trying to get us to do here? Okay, that's not good. All right.
Predict the like reactants.
Okay, so what am I looking for?
I I guess you're trying to like predict the reactants, I guess, for the thing.
So they actually just want you to draw circles and fill them in. So they want you to show that oxygen atoms are going to be in there, and then nitrogen and oxygen are going to be together. That's all they want.
Yeah.
All right, that's essentially all they're going for there. Um, so, okay, so now the tricky part is that it's a little more difficult than this. All right, so we actually have to show that there's conservation of mass. All right, so if I look over here, I have 1, 2, 3, 4, 5, 6, 7, 8 nitrogens. So I need to have 8 NOs. So I need like 8 of these. So I'll just say times 4. All right, and then I need the oxygens to balance out as well. All right, so kind of an annoying question, but does everybody understand what they're going for there? They want the number of nitrogens uh, to be equal on both sides. So if you didn't draw the exact number of nitrogens and oxygens equal, then you wouldn't have gotten that point. Okay, everybody good with that? Everybody understand what they're going for? It's kind of a silly question in my opinion, but it is what it is. Okay, student begins with an equimolar mixture of NO and NO2 in a vessel, and then we want to calculate the equilibrium constant K. All right, so how do we go about doing that part? You guys might not have had this, so we'll go over it just in case. All right, the equation that you want to use is delta G is equal to negative RT and then ln of K EQ. All right, so we have to get, we need to get the delta G or we have to be given it. So we were given it, which is good. All right, and then we just need to be real careful that our units are like in a good place. All right, so delta G needs to be in units of joules. Okay, so I'm gonna take my kilojoules and I'm gonna multiply by 1,000 to get 870 joules per mole. All right, and then I'm gonna set that equal to negative and then R. In this situation, we're dealing with energy, so that is 8.314 joules per mole. And then T is gonna be your temperature in Kelvin, so I just plug that in. And then ln of K. All right, and then for this year's exam, you should be able to just leave it like that, but I'll go ahead and get a number. All right, so K is going to be equal to, so let me just solve for it. ln of K is equal to 870 divided by negative 8.314 times 298. To get rid of the ln, I use the E. All right, so K is equal to E to this thing. All right, and when I do that, I get K is equal to 0.7. All right, is everybody okay with the calculation? Okay, great. So if both NO and NO2 in the vessel are initially 1 atm, okay, so let's remember to mute your microphones. Thank you. Where did the R value come from? Okay, good question. So do you have the sheets that they give you, that they give you for the exam? Do you have the formula sheets? Let me grab them so you guys can see them. Hang on. So in general, when you're dealing with the any of the constants, you want to make sure that your units kind of match up. So now let's see. They should give it to you, so they do. I'll zoom in so that we can actually see it, but I don't know if you guys can see this. Can you see that right there? Gas constant? Okay, so when you're dealing with energy, it's the 8.314. When you're dealing with liters, when you're doing PV equals nRT, then you use the 0.0821. All right, but for energy, you want to make sure that you use the 8.314. Okay. Any other questions on that? I would print out these sheets and really mark them up so that you know what you've got, and you're allowed to use them. So it is open. I mean, it's open notes, right? So I would have them out. Okay. Any other questions on that? Okay, great. Okay, so now we're going to be asked to find our equilibrium values. Cool. All right. Actually, we don't even need to do that. So if both NO and NO2 were in the vessel, will the pressure at equilibrium be equal to 1 atm? Okay. So here we have to sort of know that if I have 2 moles of gas, all right, and that corresponds to a pressure of 1 atm, and then I do my reaction and I go to 1 mole of gas, I want to know how many, what is my pressure going to be? Okay, so is everybody with me? How did you cancel the ln out to get K by itself? So ln is the inverse of E, so I E'd both sides. Okay, so there's 2 ways to think about this. I have 2 moles of gas at 1 atm, and then if I go down to 1 mole of gas, I should go down in pressure. All right, the exact amount that I'm going to change by is going to be determined by the equilibrium constant. All right, now if we look at the equilibrium constant itself, all right, K is equal to N2O3. Let me actually write it in terms of pressure. So it would be the pressure of N2O3 divided by the pressure of NO times the pressure of NO2. Okay, so if my K is equal to 0.7, and then let me just kind of think about this in terms of a fraction. Let's say this is 7 out of 10. All right, so at equilibrium, do I have more stuff on the top or do I have more stuff on the bottom? More on the bottom, right? So this is a reactance-driven reaction. All right, so this is not going entirely to completion, but it is going reasonably. Okay, so what does that mean for us? That means that our pressure is not going to be perfectly constant. All right, and so this is going to not be equal to 1 atm. Everybody okay with that? Okay. All right, so let me grab the next part of this. Okay, so we're going to do part D, and then we're going to skip the part that comes after it. All right, because the part that comes after it is acids and bases. So, and that's not covered for you guys. So we can just skip that one. Okay, I think that this type of a question is really fair game for you guys. So if it were me, I would be focusing on practicing Lewis structures and bonding and stuff like that. I think it's an easy question that can get answered without the use of a calculator. Okay, so the question is that we want to draw a Lewis structure for that molecule. Okay. All right, so some general guidelines here. For neutral atoms, this is a good rule of thumb for neutral atoms. All right, less of a rule of thumb for non-neutral atoms. All right, but so I'll just repeat it. So carbon really likes 4 bonds and 0 lone pairs. All right, so carbon and then everybody in carbon's column. All right, nitrogen really likes 3 bonds and 1 lone pair. All right, oxygen likes 2 bonds and 2 lone pairs. And then if you're a halogen, they really like 1 bond and 3 lone pairs. All right, so in neutral atoms, this is almost always the case. All right, so I'm going to just try and make that happen. All right, so I can make that happen by doing that with nitrogen. All right, and then oxygen would have his 2 bonds. He has his 2 lone pairs. All right, oxygen here has his 2 bonds, 2 lone pairs. All right, if you follow these rules, it's not going to really take you too far astray. All right. And then we want to know the hybridization of the nitrogen. Okay, so the way that I've always taught this, oh, you can't see what I'm doing. It's not good. Hang on a second. Okay, so there's our Lewis structure. Does anyone have any questions? Make sure I answer the questions before I go on to my little nifty trick on hybridization. Okay, so anybody have trouble with hybridization in general? I think that most teachers kind of teach it in the most confusing way possible. Not really. Okay. All right. Well, so what I'm going to do is define a thing here to be equal to a lone pair or an atom. All right. How many things are attached to that nitrogen? Where a thing is a lone pair or an atom? So 3, right? You have 2 oxygens and a lone pair. So 3 things. So for those 3 things, you need 3 orbitals. So you need S, P, and P. All right, and then I combine those to be sp2. All right, that's how you determine the hybridization. So what would the hybridization of this guy be? So you would always want to draw the Lewis structure. Determine that there are 6 things attached. So for 6 things, you need 6 orbitals, but you run out of p orbitals after the third one, so you have to reach into the d orbitals. So this becomes sp3d2 to get to 6. All right, any questions on question 2? This exam has a lot of acids and bases. Okay. All right, I'm going to skip over to 6. And then hopefully we can get through that one. How much work do they require for that part? So you would have to draw a correct Lewis structure, and then I think the answer on that is all or nothing. So if you got the hybridization, you know, you either got it right or you didn't. Okay, let's make sure we can see the screen. Can everybody see the screen? Okay, great. That's a step up right there. Okay. All right, so we're setting up a galvanic cell 298 with an electrode in 1 molar solutions, and we discover that we have no charge, right? We have no voltage. So what happened? Well, we're missing the salt bridge. So the salt bridge is there to complete the circuit. So during the course of the reaction, the anode is going to be giving off electrons and sending them through to the cathode. All right, and this stuff is on your exam. So I switched the anode and cathode. Okay, so you have an electron that's going to flow through. All right, multiple electrons. All right, and then this charge is going to build up on that cathode. So we have to add a salt bridge so that anions can flow back towards the anode. All right, so I'll just write anions go back towards the anode. All right, so from everything I can tell, electrochem is on your exam. Based on College Board's, own announcement and what they consider to be part of, different units. So the only stuff that you guys aren't responsible for are applications of thermodynamics and acids and bases and buffers and titration. Okay. We can confirm, but when I called last week, they said it was. So I called them directly. All right. So there's our